Hi folks, I'm Mr. Pinola, and while I might teach physics, it's pretty clear that I don't teach art. But nonetheless, let's take a look at a couple of the drawings I drew up for you on the whiteboard today and see how they relate to physics. The first drawing on the left is a person who is asleep. This person is very comfortable in their bed, they're asleep, maybe they're having a dream, they don't want to be woken up. Maybe you've experienced that before. Maybe somebody has tried to wake you up in the middle of the night, or your alarm clock has gone off in the morning when you're supposed to get out of bed and go to school. And all you want to do is just stay in bed and continue to sleep and get your rest. Does that sound familiar? I bet it does to many of you. That happens to me as well. When we're resting and we're inactive and we're asleep, a lot of times we just want to continue to be inactive and be asleep. However, the other picture that you see here is the complete opposite of the person who is asleep. This is a person who's running around with their friends on the soccer field playing soccer. This person doesn't want the game to end all of a sudden. They want to continue to play soccer and hang out with their friends. People who are active and are running around having a good time usually want to continue running around and having fun. When you're hanging out with your friends, you probably don't want to all of a sudden go home and go to sleep. You likely want to continue to hang out with them. Just like this person playing soccer wants to continue playing the game. But that's very different from this person who is asleep and wants to stay asleep. And these scenarios are likely something that many people experience. A lot of times in life, you may be inactive and want to stay inactive. And other times you may be active and want to stay active. So, how does this relate to physics? So, how does this relate to physics? Well, both of the people in the examples that I drew up here have something that is called inertia. Spelled I-N-E-R-T-I-A. And inertia is defined as the following. A property of matter that resists changes in motion. That's what inertia is. So let's take a look at what that definition truly means. A property of matter. Well, all objects or things that are made up of atoms are matter. We are matter as humans. And so if inertia is a property of matter, that is something that is common amongst all things in the world. And it's a property of matter that resists or does not want changes in motion. So we are resisting change. When I think about something resisting change, I think about somebody that's very stubborn, somebody that does not want to change what they're doing. For example, maybe you know somebody in your life who's very stubborn. And if you say, can you change the channel on the television? They don't want to. They don't want things to change at all. Somebody who is stubborn is sort of like somebody who's asleep and doesn't want to be woken up. They don't want to change what they're doing. It's also like somebody who's playing with their friends, who doesn't want to stop playing with their friends. They both want to continue what they're currently doing, just like objects in physics. All objects resist or don't want to change their motion or what they're doing, just like these two real-life examples. So now let's take a look at a more physics example of inertia. Here I have two pictures for you again. In each picture, we have a large truck. In the picture on the left, the truck is stopped at a red light. The truck is not moving. In the picture on the right, the truck is coming up to a green light, and so the truck is going to continue moving straight through the green light? Well, in each case, the truck has inertia, and the truck does not want to change what it's currently doing. Let's start with the picture on the left. The truck is at rest. Well, guess what? The truck wants to continue to be at rest. And that's why, to get the truck to move, the driver would have to press down on the gas pedal to get the truck to move. It won't just start moving on its own. The truck was at rest, and it wanted to stay at rest. And it would take the driver slamming down on the gas pedal to get the truck to move. But in the other example, it's the complete opposite once again. This truck was in motion and was moving through the light. This truck was in motion and it wanted to stay in motion. It did not want to stop doing what it was doing. And so if the driver wanted to stop this truck, he or she would have to slam down on the gas pedal in order to make the truck stop. So the truck at the red light, at rest, and wanted to stay at rest, did not want to change what it was doing. The truck coming up to the green light, in motion, and it wanted to stay in motion. It didn't want to change what it was currently doing. These are both examples where the truck has inertia. The truck is resisting or does not want to change what its motion currently is. It wanted to stay at rest in this picture, and it wanted to stay in motion in this picture. Did you see what just happened there? Let me show you one more time. Here, I had a large lid to a plastic container, and I placed a volleyball on top of the lid. I held the lid out in front of me at rest. The volleyball was at rest. But then I started moving. And the volleyball fell off the lid and went straight down. Why did that happen? Well, let's think about what we just learned about. The volleyball is an object. It has inertia. And so, at the start of my example, the volleyball was at rest. And it wanted to stay at rest. But when I started moving, the volleyball still wanted to stay at rest. And so it stayed at rest while I moved. And that's why it rolled off the back. Watch the volleyball stay at rest while I move. It basically fell down right in the middle. It was staying at rest even though I was the one moving. That's an example of inertia, an object at rest wanting to stay at rest. But now that was a bit of a different example. This time, the situation was different. Let me show it to you once again. I'm going to go off screen, but you're going to see me walk across your screen once again. How is that situation different? Well, this time, I was in motion with the volleyball. The volleyball, me, and this container lid were all moving in this direction. But then I suddenly stopped. Did the volleyball want to stop? It didn't. And so it continued to roll forward. It was continuing to be in motion. So even though I stopped and the lid stopped, the volleyball rolled forward off the edge of the lid. Let me show it to you one more time so you can get a clear sense of the volleyball wanting to stay in motion. Here it is again. We say this example is explained just the same way as the last one was. The volleyball has inertia. This time it was in motion and it wanted to stay in motion. Last time it was at rest and it wanted to stay at rest. But both cases are examples of inertia because the volleyball does not want to change what it is currently doing. It's stubborn. Now, this was a huge discovery at the time, made by a man that you may have heard of before, Sir Isaac Newton. And Newton discovered that objects wanted to continue to stay at rest if they were already at rest, and they wanted to continue to stay in motion if they were already in motion. And so Newton proposed what became known as the law of inertia. Basically saying that objects wanted to continue doing what they were already doing. That's basically what inertia means. However, this name didn't quite stick. Newton gave his law a more formal name, and he called it Newton's first law of motion. Newton's first law of motion is the same thing as the law of inertia. So let's take a look at what the law says. Newton's first law of motion, which I'll underline now. Action 1. So let's take a look at what Newton's first law of motion actually says. The first law has a couple of parts to it, and I'll use different colors to show you those parts. The law says that an object at rest will remain at rest. That was sort of like the person sleeping. They were at rest and they wanted to stay at rest. And an object in motion will remain in motion. That was sort of like the person playing soccer. They were moving around, they were in motion, they wanted to continue to be moving around. Unless, and this is where it gets a little tricky, acted on by an unbalanced force. An object at rest will remain at rest, and an object in motion will remain in motion unless acted on by an unbalanced force. So when you think about Newton's first law of motion, which there are 3 laws of his that we'll learn about, you should remember that there are 3 different parts to it, and make sure you say all parts of the law. The first part, which I have in blue, talks about objects that are at rest. The second part, which is in green, talks about objects in motion. And the last part, which is in red, talks about what would have to happen to get these objects to stop being stubborn, to get them to actually change what they're doing, because otherwise they're just going to continue doing what they're already doing. So objects at rest want to stay at rest. Objects that are moving want to stay moving unless there is an unbalanced force that acts on them. Let's take a look at some examples that show how this last part in the red actually works. So let's take a look at the fact that an object that is at rest can actually change what it's doing if there's an unbalanced force that acts on it. You see that whiteboard all the way down there at the end of my kitchen? That whiteboard is not moving. It's at rest. It wants to stay at rest. That means that the whiteboard has, you guessed it, inertia. Remember, all objects have inertia because any object that's at rest has inertia that causes it to want to stay at rest. And any object that's moving has inertia because that inertia wants to keep it moving. But this whiteboard has inertia because it's at rest. There are two forces right now acting on the whiteboard. You know what they are? Well, the force of gravity is pulling it straight down. And the normal force from the ground is keeping it balanced. So the forces on the whiteboard are currently balanced. But if I pull the whiteboard towards me, then I will be applying an unbalanced force. My force will not be balanced by any other forces. I'm going to pull with so much force that it will be bigger than the amount of friction that could act on it. And so if I pull with an unbalanced force, then I will get the whiteboard to change what it's doing. And I will cause it to not be at rest anymore, even though it wants to be. So let's do that. I'm going to apply an unbalanced force to that whiteboard. And that's exactly what happened. The whiteboard had inertia. It wanted to stay at rest. But since I applied an unbalanced force, I was successful in getting the whiteboard to go from being at rest to being in motion. Now let's take a look at another example of inertia. But this time, we'll take a look at the opposite kind of example. Now we're going to look at something that is in motion, that we need an unbalanced force to stop. That object that's going to be in motion is me. I can move around every which way, and I will be in motion. But I'm going to move in a straight line towards that wall on the side. And if I move in a straight line towards that wall, I will be in motion. And my body is going to want to continue to be in motion. But guess what? I'm not going to be able to run through that wall. And so that means that the wall will have to put an unbalanced force on me to cause me to stop, to cause me to change my motion. Let's have a watch. I'm in motion, and I crashed into the wall. And that's because the wall applied an unbalanced force that caused me to not be in motion anymore. Maybe you've experienced a case where somebody has tripped you. If you're moving and somebody trips you by hitting your leg, then you might go toppling over. And that's because you were moving and something tripped you, but the top part of your body continued to move forward. Objects that are in motion want to continue to be in motion, just like the human body does, just like me. So, if I was to put a chair in my way and then continue to move towards the wall, the chair would stop my lower body, but my upper body would flip over and I would fall face forward into the wall. That's because now the chair would be the unbalanced force that stopped me. Before, it was the wall that applied the unbalanced force to get me to stop. But either way, I was an object in motion. My body wanted to stay in motion, but an unbalanced force from the wall or from the chair could get me to not be in motion anymore. Let's consider one last example of inertia. On the screen in front of you, you see two football players. Maybe you recognize the player on the left side of your screen. That player, wearing number 75, is former New England Patriots defensive lineman Vince Wilfork. Vince weighs well over 300 pounds. He's a big guy, but he's also pretty fast. His job is to get after the quarterback and to run through the offensive line from the other team and tackle the other team's quarterback. The player on the right is a player at Desert Shores High School in Nevada. This player's name is Darnell. He's wearing the number 1 jersey. Darnell has the same job as Vince Wilfork. He's on his high school team's defensive line. And Darnell is also really fast. In fact, he's about just as fast as Vince is. you will notice from the picture that Darnell is much smaller than Vince. And as a result, it is going to be much harder for the offensive line to stop Vince than it will be for the offensive line to stop Darnell. Vince on the left here will be really hard to stop because he is in motion and wants to stay in motion. Darnell is also pretty hard to stop. He's a good defensive lineman. And so he is hard to stop because he is in motion and he wants to stay in motion. But as you can imagine, Vince is the much more difficult of the two players to stop because not only is Vince just as fast as Darnell, but he's also bigger. And so objects with more mass are more difficult to stop. What does that mean? Well, that means that if an object has more mass, it has more inertia, and it is more likely to continue doing what it's already doing. So what did we learn from that example? If you have more mass, that means that you have more inertia. That's why it's harder to stop a bigger football player than a smaller football player running at the same speed. And that's why it's also harder to stop a big truck moving down the highway than it is to stop a small car moving down the highway at the same speed. More mass means you're more likely to continue doing what you're already doing. And that means that you have more inertia. Before we head off today, I want to show you one last example. These might look like two similar boxes, but they're full of very different things. This box that I'm leaning on is very massive, and that's because there's a lot of stuff in here. There's board games, there's books, there's bookends. There's a lot of different objects in here. And so this is a really, really massive box. It weighs a lot as well. This box is empty. There's nothing inside of it. So even though it might have the same volume, this box has much more mass than this box. So which box is better at staying at rest? Because right now, both of these boxes are at rest on the two chairs. They don't want to move. They don't want to change their state of motion. As you can tell, this box here has more mass, and therefore, if you remember what we just said, it has more inertia. It's better at continuing to do what it's already doing. So I'm going to try to lift this box. I am going to be the unbalanced force that changes its motion. It's at rest. It wants to stay at rest. But because of my unbalanced force, I'm going to get it to change its motion. I'm going to get it to go from being at rest to being in motion. So let me lift it. It's pretty difficult to lift. This is a pretty heavy box. And so if I were to lift it all the way over my head, that takes a lot of energy to do. But this box, it's also at rest. It wants to stay at rest, but it doesn't have as much mass. So my unbalanced force is going to get the box to change its motion really easily. Have a watch. I can almost throw this box up in the air and catch it because of how easy it is to get it to change its state of motion. This box has very little mass and therefore very little inertia, and so it's bad at continuing to do what it's already doing. This box, a lot of mass, a lot of inertia, and it's very good at continuing what it wants to do. So remember, folks, Newton's first law of motion is also known as the law of inertia. And it says that if you have an object at rest, that object will want to remain at rest. And if you have an object in motion, that object will want to remain in motion, unless there is an unbalanced force that is applied. That will cause resting objects to no longer be at rest, and it will cause objects that are in motion to no longer be in motion. Thanks for watching today, folks.